Hello everyone, my name is Ana Maria Ruiz and today I am going to be presenting my project called Detecting Fake Job Posts. So for this project we are going to use the employment scam agent dataset from the University of the Aegean. This dataset is also hosted in Kaggle here and we are going to use this version. This dataset contains information about job posts in a website, and the idea of this project is to use that information and classify it to identify the fraudulent job posts and the ones that are not fraudulent. This is something really important because nowadays we all apply for jobs through websites, and when there is a legit company behind the post, it is a good thing. We can get a job, we can go through a hiring process maybe, but when it doesn't happen, we are exposing a lot of personal information, maybe a possible identity theft, or maybe we can be exposing our information to spam, unwanted emails, or even something worse like a traffic network. Uh, so that's why identifying the job posts that are legit and the ones that are not is a really important thing, and I wanted to approach it in my project. Now let's start looking at the code. The first thing that we are going to do is load our data set and also look at the summary of it. This data frame has around 17,880 observations and 18 variables, which include also the outcome. As we can see, we have the job ID, things like the title of the job post, the location, or the department of the job post, the salary range, but we also have a lot of text in it, like the company profile, the description, or the requirements. But we also have some data that is already categorized, like telecommuting, or if the company has a logo or not, or if it has questions. And at the end, we have our outcome, which is called fraudulent, and it is going to identify with a 0 if the job post is not fraudulent, and with a 1 when it is fraudulent. So the next thing that we are going to do is to explore our data. As we can see, most of our data text and categorical. So what we are going to do is explore it using bar plots. Something that we are going to ignore from our whole data set from the beginning is the job ID, because it is just an identifier of the job post, so it doesn't add anything extra to actually predict. So we can see here that first is that we want to identify all the unique values that we have per each variable, and we can see here including the text. So as we can see here, for example, in the description we have more than 14,000 unique descriptions and more than 10,000 unique titles, but in the case of the data that is already categorized, we have really low values. They are not even able to appear here because we have just 2 levels in those features. If we continue with our visualizations, here we have another bar plot that shows the percentage of missing values that we have per variables, and we can see that there are variables that have more than 40% of missing values, like in department or in salary range, are in required education. Those are things that we have to consider also when we are going to do our data cleaning and selection of features. Then what we are going to do is to check at the distribution of our data again, but now we are going to exclude all the text. As we can see here, we have more than 10,000 unique values for a title, and if at some point we consider them as levels of the category without doing something, we are going to end up with a lot of features, and we don't want that in our model. So the next step was to try to identify how distributed is the fraudulent and the non-fraudulent cases per variable and each possible level of the variable. The first try was in industry, but it has a lot of unique values, so definitely it's hard to read. We try again with required education, and in required education is easier. We also can see here in pink all the data that is non-fraudulent, and in sky blue the ones that are fraudulent, and we can see that actually most of our fraudulent cases are related with missing data. The same is happening with required experience. A lot of missing data contains also a lot of observations that are considered fraud. Now what we are going to do is to clean the data. So to clean the data, first we are going to erase the department salary and required education, which are the ones that have more than 40% of missing data. And now we can see here the percentage of missing data that we have per feature. And the type of imputation that we wanted to do here was in how our classes are not well distributed. Definitely using the mode is not a good technique to fill the missing data. So what we are going to do is create a new category that is going to call unknown, and this is going to be a new categorical level that is going to be in all the missing data. And after doing that, we are going to see that now we have all our data set clean. Another feature that in which we are going to perform a feature engineering, because we can actually take advantage of the location to identify the places where we can find more fraudulent job posts. We can see here what happens after we divide it in regions. Actually, the North America region is also the one that contains the most occurrences of the fraudulent job posts. So we reduced our categorical levels, but we kept the trend that, of the location. So the next thing that we are going to do here is to check the correlation of our categorical data. But because this is categorical data, we have to be careful, and what we have to use instead of other tests that we usually use is to use the chi-square test. And here in the chi-square test, we can see that looking at the p-values, those are actually really low, and this is telling us that our data is highly correlated. So there is no option like to choose the ones that are not correlated, to take them out of our data set. But the next step that we are going to do is to erase the title and the industry from our data frame, because especially in the case of the title, is working almost as an identifier, and it is going to add a lot of possible new features to our model, and we don't want to work with so many variables. So the next thing that we are going to do is to perform the MCA analysis. As we told previously, the MCA analysis is actually the alternative for the PCA analysis, because here what we have is not discrete values but categorical values, and we are going to perform this analysis because it is necessary. So what we are going to do instead is to actually create the dummy codes for our dataset. And now what we are going to do is to divide our dataset in three sets. The one is the training dataset, the other one is the validation dataset, and the testing dataset. Then what we are going to do is to create a data frame where we are going to save the information about the model, the accuracy, and the IUC. And also what we have here is a function that is going to be used in some of the models. It is going to give us the option to show a confusion matrix, the accuracy, and so now let's continue with training our models. The first one that we are going to use is the naive Bayes, and we are using the naive Bayes because this is the one that the first one that we think when we usually are dealing with categorical data and with classification. Actually, the theory tells us that it is really good for working with text. But after the training and even using the Laplace to tune the model, we can see that we have a really bad performance. Actually, it is not. It is classifying all the fraudulent ones, but is having a lot of problem identifying the legit jobs. So definitely we are having troubles here. And one of the things that we may have to remember is that naive Bayes always assumes that the features are independent. The next one is going to be the random forest. I decided to change from implementing neural networks and logistic regression to use instead the random forest because it is actually a good model that works well with again categorical data, and it's used for classification. So we are going to see what happens with this one. So now let's go to the confusion matrix of our model, and we can see that with our testing dataset, it is working actually good. It is identifying most of the legit ones, but it's having problems when it is trying to identify the fraudulent ones. But it is still better than working with the naive Bayes. And now the next one that I am using is KNN, because KNN is also a really good one and easy to implement if we may consider that we are doing a classification. We are working with categorical data, so as this is all categorical data, we don't have to worry about scaling our data. And at the beginning, I thought that it was supposed to be like easy to implement this one, so I use a value of 3 for the K, and we can see that actually it is performing good. So until now we can say that this is our best implementation. Now the next step is going to be to use k-folding to see if there is an improvement in naive Bayes. We are going to again try to see if there is a way to make it work better. And for naive Bayes, what is happening is that this time is identifying better the legit ones, but is doing really bad with the fraudulent ones. So what does it mean? That is identifying all of them as legit. So there is not improvement at all with our model. Now let's do the same with a random forest and see what happens. So we can see here that actually random forest improve a lot if we compare it with the previous implementation, because now it is also identifying more fraudulent cases than actually classifying them as legit. So the next step is going to be to implement KNN with K folding. So as we can see here, this time we are going to implement bagging. In this case, we are going to use bagging just on naive base and KNN, because random forest is already implementing bagging. So we can see here the confusion matrix of our naive base. Again, it is doing really bad. What it is doing is classifying all of them as legit and not being able to identify the fraudulent ones. So bagging is not helping our model. Now let's make it run for a KNN, and again, as we can see here, KNN with bagging still keeps a good classification of the legit and the fraudulent ones, but it didn't improve if we compare with the previous ones. So what we are going to do now is to create an ensemble model. This ensemble model is going to be a stack one, and it's going to combine three models: the naive base, the random forest, and the KNN. So what we are going to use here is weighted average. This weighted average, it has a low value for a low weight for naive base, because it is the one with the worst performance, and we are using actually a higher one for a random forest and KNN, because those are the ones that work better. And then we are going to get our we are going to identify the legit ones and the fraudulent ones from our weighted average prediction, and we are going to return that. Here is where we call our ensemble and make the prediction, and after that here we are going to create our confusion matrix and store the accuracy and the AUC in our data frame. So here we can see our confusion matrix of the ensemble model, and we can see that it's actually really bad. It's happening the same as with the naive base, because it is identifying all of them as legit and is not actually classifying our data set. So what we have to consider here is that definitely when we combine the models, if we have a really bad one, it is going to affect the others no matter how good they are. And here is when we finally do our evaluation. What I did was, in a recall, I put all the accuracy and AUC values in a data frame that I call model evaluation, and later I did this plot. And this plot is first to identify the accuracy. And why to insist in the accuracy? Because sometimes we may think that accuracy is enough, but it is not the case when we are doing a classification. This could be actually misleading. If we remember, naive base was doing really bad, and if we think just in accuracy, we can think that the first one was the bad one, and when we apply folding and bagging, we actually make an improvement because the accuracy was higher. But when we check at our confusion matrix, we realize that it was not the case. So definitely it is a really misleading metric in this case for classification, even though if it is good for random forest with K folding, we shouldn't trust an accuracy. However, the IUC is actually a better because, as we can see here, our ensemble and our naive base, all the implementations are in 0.5, which means that basically what is happening is that our model is not classifying, it's just guessing the values for the classification. So, but if we go to look at the random forest with k-folding, which was the best one that we could see from the confusion matrix, it is also the one that has the highest value for the AUC. So definitely for classifications, we have to consider other ways to evaluate besides the accuracy. And the AUC is actually a good one that reflects the real capacity of our model to perform a classification. So from this, I think I got really important lessons. The first one is that the treatment of our dataset previous to the modeling is really important, especially when we have categorical data. This is my first time working with all categorical data, and we know the good reputation that naive Bayes has for classification in general and working with categorical data, but we have to remember that the model says that it also assumes that all the features are independent, and in this case we have a highly correlated data set, so definitely it is going to go against all the assumptions that it is doing naive Bayes, and it's going to perform really bad on our data set. And when we are cleaning our data set, and especially when we think about the treatment of missing values, we don't want to erase our missing values, and what we are going to do usually is try to find a way to fill those missing values, for example using the mode, or maybe trying to use a regression. And this, what is going to happen is that our model is going to be our data set is going to be more correlated, so definitely it is going to perform really bad with naive Bayes. So when we have to choose the model, definitely in this case we have to ignore it, and we can choose actually another ones like random forest, which has a good reputation, but also this one doesn't have a lot of problem with the correlation of the data. Also, another really important lesson for me is that we have to, when we do an ensemble, we don't have to assume that the ensemble is going to work well just because we choose the best models, or even if we have like two good ones, it is going to actually erase all the work, and is going to defeat the bad predictions of a weak one that is really bad implemented. So we have to be careful when we create an ensemble, and even if those are weak ones, combine the ones that are actually doing a real prediction, and not in the case of this combination that used two that were doing a good work and another one that was definitely not working at all.